Welcome back to the Deep Dive. Today we are strapping ourselves into the world of elite competitive engineering, specifically Formula Student electric FSE racing.
It's a fascinating
It
space.
really is. But we aren't here to talk about carbon fiber or aerodynamics today. We're talking about the brain of the race car, the, uh, the digital architect that really dictates victory, the vehicle control unit.
The VCU, absolutely central to everything.
We've been handed a world-class strategic engineering document, a blueprint for success, called the VCU 3.0 specification. This is basically the definition of best practices, and it's custom-tailored to help a brand-new university team skip years of painful trial and error.
And jump straight to a competitive world-class architecture. That's the goal.
Exactly. So our mission here is to unpack this high-level strategy for you, the listener, and define what it actually takes to win in this new era of software-defined vehicles. Okay, let's unpack this.
Where do we begin?
Well, the strategic landscape in FSE has fundamentally transformed, hasn't it,
Right.
over the last decade or so?
Oh, completely. It's a different world.
Right. Because back in the day, the teams that won were the manufacturing powerhouses, the ones who could pull off an amazing carbon fiber monocoque or build the most aggressive aero package.
That's the critical shift we identify in our consultancy work. The competitive edge has moved entirely. It is no longer just about the hardware you can build, but the intelligence that controls it.
So the marginal gains from that pure mechanical hardware, they're reaching a definite limit.
They are. The competition core has shifted from hardware manufacturing to the software-defined vehicle, or SDV, and the control intelligence that governs every single millisecond of driving.
So this VCU 3.0 specification, you see it as a mandatory paradigm transition.
It is. We are moving away from what we call reactive control, which are systems designed to fix a problem after it's already happened, to predictive control. And, just as importantly, deterministic communication.
Reactive versus predictive, that feels like the core philosophical shift right there.
It is. A reactive system is always losing time. A predictive system is always gaining it.
And you've distilled this whole strategic vision into three main pillars, right?
Yeah.
For dominating the dynamic events, especially autocross and endurance.
That's right. Because success in four-wheel electric drive is, at its heart, a software problem. The first pillar is determinism.
Okay, determinism, that sounds precise.
It is. This isn't just about speed, it's about predictable speed. We require microsecond-level synchronization. We're talking less than 1 microsecond of jitter.
Wow. Okay, why?
Mhm.
Why is that level of precision needed?
Because in a four-wheel independent drive system, if the left front and right front wheels receive a command for differential torque, to create a yaw moment, and one of them executes it even 3 microseconds later than the other, you've instantly induced an undesirable lateral force.
Okay, let's stop there. Less than 1 microsecond. That's an almost unimaginable scale. If a car is moving at, say, 100 kilometers per hour, what does that delay even look like physically?
Well, at 100 kph, the car is moving about 28 millimeters every millisecond. But what's more relevant is the time constant for a tire to develop significant lateral force when it's pushed past its slip limit. That's often in the 10 to 50 millisecond range.
Right.
So if your torque vectoring command is jittering by 100 microseconds, that's 100 times worse than our target. And that jitter, applied across 2 opposing wheels, creates these momentary high-frequency torque imbalances.
And what does the driver feel?
They feel it as torque steer. It forces the driver to constantly make these tiny, counterintuitive corrections with the steering wheel. It completely erodes their confidence and, crucially, their speed. Determinism just eliminates that noise.
Okay, so pillar 1 is determinism. What's number 2?
The second pillar, and this is the core intellectual challenge, is optimality. This is where we formally reject PID control.
The old standby.
Exactly. We mandate the transition to Model Predictive Control, or MPC. The entire purpose of MPC is to resolve real-time dynamic conflicts optimally.
Give us an example of a conflict.
A great one is when you're cornering right at the limit. The driver wants the maximum possible yaw rate, but at the same time, you have to respect the absolute dynamic limit of the tire's grip. A traditional control system can't solve that trade-off. It will either prioritize one or, more likely, fail at both. MPC solves for the optimal outcome that minimizes both error sources simultaneously.
So we're trading the simplicity of something like proportional control for the holistic complexity of predictive math, all to gain speed and stability.
Precisely. And that brings us to the third pillar, resilience. Performance only matters if you finish the race.
The first rule of racing.
It is. The VCU 3.0 must adhere strictly to the highly unforgiving safety rules. I'm talking about FSGT 11.9 on power shutdowns and EV 5.8 on plausibility checks. Resilience means ensuring continued controllability or, if that fails, performing a guaranteed safe and immediate shutdown the moment a critical sensor fails.
So this is the difference between losing a few points and a catastrophic shutdown that just ends your event.
Exactly. That's the whole strategic vision in a nutshell.
That philosophical shift determinism, optimality, resilience, it must force a complete rethink of the physical layout, the architecture.
And it does.
Our sources are very clear. You have to abandon the legacy flat CAN bus topology. Why was that such a problem for older teams?
The flat CAN bus was the death knell for so many systems once they started pushing performance. Imagine trying to hold a highly technical conversation in a room where 50 people are all talking at once about completely different things.
Okay, I can picture that. Chaos.
That is the flat CAN bus. Every single component, from the low-priority dashboard status light to the safety-critical brake pressure sensor, was competing for the exact same limited bandwidth.
And I assume that created unpredictable delays.
Unacceptable and unpredictable delays. As soon as a high-frequency sensor like a 1 kHz IMU was added or data logging increased, the network load just skyrocketed. This completely violates our determinism requirement.
So what's the solution?
VCU 3.0 must mandate a dual-domain isolation architecture. This physical segregation is the only way to meet the vastly different demands of bandwidth and latency that the system requires.
Okay, dual domain. Let's start with domain A, the powertrain domain. This sounds like the nervous system running on pure adrenaline.
That's a good way to put it. Domain A is dedicated to hard real-time control, and the term hard real-time is absolutely crucial.
What does that mean specifically?
It means if a deadline is missed, let's say the VCU calculates the optimal torque command, but the inverter receives it 1 millisecond late, the resulting vehicle instability could be catastrophic, especially during a high-speed corner. The performance of the car just collapses.
So the specs here have to be non-negotiable.
Completely. Cycle time must be 1 millisecond or 1 kilohertz. That rapid update rate is essential to keep up with the fast dynamics of the vehicle. Think about how quickly wheel speeds change under traction control. And, as we said, the jitter has to be strictly less than 1 microsecond.
And that tiny jitter requirement is what forces you toward these highly specialized communication protocols.
Exactly. The protocol has to inherently support synchronization. This is why EtherCAT is the preferred choice. Specifically, we need to leverage its distributed clocks feature. The whole structure of EtherCAT is engineered for this level of determinism.
What about alternatives?
Well, a proprietary high-speed CAN FD might be a fallback, but it adds a huge amount of complexity and risk. EtherCAT is really becoming the established global standard for this kind of high-performance control.
So what components have to live in this high-speed, safety-critical domain?
Everything that directly affects the immediate dynamic stability of the car. So that's the 4 inverters, which are receiving the torque commands, the high-precision inertial measurement unit, the IMU, providing critical data on acceleration and yaw, and of course the VCU master itself, which coordinates everything. The data here is performance critical.
So if domain A is the high-speed lane, domain B, the body domain, sounds more like the general-purpose road. All about compatibility.
That's a perfect analogy. Domain B operates under what we call soft real-time.
Meaning a delay is an inconvenience, but it won't crash the car.
Precisely. Maybe the dashboard updates a bit slowly, but the car is still stable. Its main priority is compatibility with commercial off-the-shelf components, COTS parts, which often have fixed, older communication standards.
So we're talking about much looser tolerances here.
Much looser. Cycle times can be anywhere from 10 milliseconds up to 100 milliseconds. The jitter allowance is up to 1 millisecond, 1,000 times larger than domain A.
And the protocol of choice is just the old standard.
Naturally, standard, classic, CAN 2.0 because it's the lingua franca for the majority of automotive-related peripheral devices. This is where you put your dashboard display, your physical pedal sensors, the APPS, your battery management system, the BMS.
So the BMS sends status updates like temperature and state of charge.
Right. And the insulation monitoring device, the IMD, and steering wheel sensor inputs, all that lives here.
And the key strategic value of this isolation is just to prevent interference.
It's a risk mitigation strategy, fundamentally. If the BMS decides to send a sudden, massive data dump, say, a minute-by-minute log file, that huge burst of traffic on the CAN 2.0B bus must not spill over and corrupt the timing of the critical torque commands being sent over EtherCAT.
The dual domain structure is basically a firewall.
A digital firewall, exactly.
Okay, this brings us to the actual hardware. The critique is clear that your average low-end microcontrollers are just not going to cut it.
Not even close.
And that's because this whole VCU 3.0 strategy is built on Model Predictive Control, which means solving some really complex math problems in real time. What kind of computational horsepower are we actually talking about here?
We are talking about performing computationally intensive tasks. You're solving quadratic programming or QP matrices hundreds of times a second. This requires extremely efficient number crunching.
So you need a powerful floating point unit, an FPU.
You need an FPU and ideally a multi-core architecture to handle parallel tasks. You're running the control loop, managing the EtherCAT communication, and executing safety monitoring all at the same time. A standard 8-bit or 16-bit microcontroller just chokes on that workload. You need 32-bit automotive-grade processing minimum.
For a new team, this sounds daunting. Where's the biggest risk?
The single biggest time sink is getting caught up in low-level embedded software development. So the recommended shortcut is what we call rapid control prototyping platforms, or RCPs.
Let's talk about the trade-offs there. The document recommends a preferred solution.
Our preferred path for maximum speed to performance is the SpeedGoat mobile real-time target. The strategic value here is its seamless integration with a model-based design environment, specifically MATLAB and Simulink.
So you can design the whole thing visually and then just click a button to deploy it.
It's very close to one-click functionality, yes. The code is generated and deployed directly. This just dramatically shortens the development cycle.
And it has other hardware advantages.
Yes, SpeedGoat units often come equipped with powerful field programmable gate array modules, FPGAs. This is vital. The FPGA can handle the heavy lifting of protocols like the EtherCAT master stack and hardware, which frees up the main processor for the important stuff, the MPC computation.
So for a new team, avoiding the headache of writing custom hardware drivers is a massive advantage.
It's an immediate, massive competitive advantage.
What about the other option, the industry standard? I know a lot of big automotive firms use DSpace.
The alternative is the DSpace Micro Auto Box 3, and it is, without question, the automotive industry gold standard. It's known for extremely stable, robust I/O and superior debugging tools.
But there's a catch.
There's a big catch for a student team. The economics are challenging. The initial hardware cost is often prohibitive, and more importantly, the ongoing mandatory licensing fees for the software tool chains add a significant, often recurring financial burden.
Which just kills a team's budget flexibility.
It can. So the trade-off is superior stability versus sustainable cost and integration simplicity. For a new team, SpeedGoat almost always represents the optimal balance point.
What was the long-term goal? After a few years, do they stick with the RCP platform?
Looking to the long term, if the team stabilizes and develops deep technical expertise, specifically strong embedded C and C++ skills, they should transition to a dedicated embedded target, something like the Infineon RX TC3XX series.
And what's the advantage there?
The TC397, for instance, is true automotive-grade silicon. It's A-SIL-D capable. It has a multi-core, tri-core architecture. It's perfect for parallel processing. You can handle communication tasks on one core and the control algorithm on another.
So the goal is always to move to custom embedded silicon eventually, but only when the team has the maturity to handle that complexity.
Exactly. And the major caveat, which must be drilled into a new team, is the risk of getting bogged down. If you attempt the Infineon Oryx route without senior embedded engineers who can write low-level drivers, you risk spending an entire season just getting your CAN bus to work instead of perfecting your MPC controller.
It's a strategic choice. SpeedGoat for fast iteration, Oryx for long-term optimization.
Exactly.
It's clear that the hardware is just the vessel. The real goal is world-class communication performance. And this VCU 3.0 is built on a mixed topology, EtherCAT for high-speed outputs, CNFD for high-bandwidth sensor inputs.
The communication layer dictates the entire system's potential. If your nervous system is slow, your reflexes are slow. You just can't run a 1 kilohertz control loop if your communication latency is consistently 2 milliseconds. It's impossible.
So let's talk about EtherCAT, the deterministic nerve center. You said the requirement for four-wheel drive is that all 4 inverters have to execute the command within the same microsecond.
It's an extreme requirement, but a necessary one.
Yeah.
If the torque is applied unevenly, even for a moment, you induce a self-steering effect. It undermines the entire stability system.
So how does EtherCAT achieve that level of simultaneous execution when the command has to physically travel to 4 different points on the car?
The key is its patented technical principle, processing on the fly.
Processing on the fly. Okay, so what does that actually mean?
Well, unlike standard Ethernet, where a data packet is received at a node, stored in a memory buffer, processed by software, and then forwarded, which introduces all sorts of unpredictable delays,
Right.
EtherCAT data frames pass through each slave device, each inverter, like a train through a station without stopping. The hardware inside the inverter directly reads or writes the necessary data while the frame is still in transit.
Ah, so it eliminates that storage and forwarding delay at every node.
Exactly. That allows for ultra-low cycle times. But speed isn't enough. We need that synchronicity. And that brings us to distributed clocks, or DC.
Tell us more about distributed clocks. How are you ensuring 4 physically separate devices are synchronized to less than a microsecond?
I think of it like a networked GPS system, but just for timing. The VCU master sends out a specific reference timestamp. Each slave device then measures the precise time it takes for that reference signal to arrive and calculates the exact transmission delay unique to its physical location on the network.
So it knows how long the wire is, essentially.
Essentially, yes. It then compensates for its own internal clock drift based on this network-wide time. The result is a system where the torque response synchronization error, the jitter, is absolutely maintained below that 1 microsecond threshold.
And that's the difference between a high-performance system and a world-class system.
It is. It eliminates those parasitic torque disturbances that destabilize the car when you're cornering right at the friction limit.
Okay, that handles the outputs. Now let's look at the inputs. A lot of high-quality off-the-shelf sensors don't speak EtherCAT. They default to CAN. Why is the old standard CAN 2.0b a problem for integrating those sensors?
The problem with classic CAN 2.0b is the data payload limit. It's tiny, only 8 bytes per frame.
It's just 8 bytes.
And that forces you to fragment complex, crucial sensor data. Think about the 6-axis IMU data, 3 accelerations, 3 angular velocities. You can't fit all of that, especially with high-precision numbers, into 8 bytes.
So you have to split it into multiple packets.
You do. And when you split that data into 2 or 3 separate packets, they arrive at the VCU sequentially, not simultaneously. This is called time skew.
So the VCU gets the yaw rate, and then a fraction of a second later, it gets the lateral acceleration.
Exactly. And your sophisticated MPC algorithm, which is designed to calculate vehicle state, is now working with a temporally inconsistent snapshot of the vehicle. The integrity of your vehicle model just instantly degrades.
And CNFD solves this simply by increasing the payload capacity.
It's the necessary solution. CANFD, or flexible data rate, dramatically increases the payload capacity to 64 bytes per frame. This allows the entire vehicle state vector, your brake pressure, your steering angle, all 6 IMU axes, to be bundled and transmitted in a single synchronized frame.
So the VCU can trust that all the data points it's using for its calculation came from the exact same slice of time.
Precisely. And for the specification, we require the data phase baud rate to be set high, between 2 and 5 millibps. But here's the crucial part. We must strictly control the bus load to under 60%.
Why under 60%?
Because if the bus load gets any higher than that, the probability of message collisions and delays increases exponentially. You end up reintroducing the exact latency and unpredictability you were trying to avoid in the first place.
This brings us back to the role of the VCU as the central gateway. It has to be the traffic cop.
It absolutely does. It's handling the high-priority EtherCAT traffic, the high-bandwidth CANFD sensor data, and the low-priority slow CAN 2.0b traffic from all the other peripherals.
Right, because the reality is, many components like the BMS or pedal sensors still rely only on classic CAN 2.0b.
It's a compatibility reality, which is why that isolation requirement is so paramount. The body domain traffic, all the logging, the dashboard updates, it must be logically and physically prevented from interfering with the real-time control of the powertrain domain.
So how is that enforced inside the VCU's processor?
It's enforced through internal priority scheduling. It is a mandatory technical requirement that the tasks handling the EtherCAT communication and the MPC computation are assigned a higher interrupt priority than any standard CAN 2.0 task.
So if a CAN message is being processed and a critical EtherCAT interrupt fires,
the CAN task must be immediately preempted, pushed aside.
Yeah.
This hardware-level priority enforcement is the digital firewall that ensures safety and performance deadlines are always met.
Okay, this is where we get to the intellectual competitive advantage, the big shift, moving from the familiar PID control to the complex predictive world of MPC. For a new team, that's a massive learning curve. So why is this necessary? What is so wrong with PID control?
It's a matter of dimensionality and constraint. PID is taught universally because it works beautifully for simple, single input, single output systems, SISO systems, like controlling cruise speed or the RPM of a single motor.
But a four-wheel independent drive FSE car is not a simple system.
It is a complex, multi-input, multi-output, or MIMO system, and that's where PID fundamentally fails.
So what's the primary failure mode?
It stems from the SISO challenge. The PID controllers are effectively blind to each other. They operate in total isolation, each one focused only on minimizing its own error, with no knowledge of the greater system state or what the other controllers are doing.
I still struggle to visualize what that means in a real-time race scenario. Can you paint a picture of where PID actually fails?
Absolutely. Let's imagine an aggressive cornering situation. The driver turns in too hard and the car begins to oversteer. The rear end starts to slide out. The yaw PID controller, which is tasked with stabilizing the car, correctly sees this excessive yaw rate and tries to fix it by instantly reducing torque on the outer wheels.
Okay, that makes sense. It's trying to create a counter-yaw moment.
Right. But at the exact same instant, the longitudinal slip rate PID controller that's monitoring that outer wheel detects that the wheel speed is falling rapidly because of that torque reduction. From its narrow point of view, it thinks the wheel is losing traction.
So it tries to fix that problem.
It does. Fulfilling its single mandate, it decides it must increase the torque to bring the slip rate back to its target. The two controllers are now directly fighting each other.
An internal war.
Exactly. Creating oscillation, instability, and a sudden, uncontrollable moment of slip. We've seen competitive vehicles spin out during autocross simply because their controls were fighting themselves. It's a strategic failure.
And beyond that internal conflict, PID has other weaknesses.
It suffers from severe constraint blindness. It cannot mathematically incorporate physical boundaries like the tire's grip circle or the maximum battery current. If the controller demands 100 newton meters of torque, but the motor can only safely deliver 80, the PID just relies on hard concation. It just chops the output at 80.
And that leads to integrator windup, which makes the whole system sluggish.
Precisely. The integral term of the PID keeps accumulating that 20 newton meter error, building up a massive unrequested command. When the constraint is finally removed, that huge integral term suddenly unleashes a massive torque spike, causing unpredictable behavior and instability. It's just inherently reactive and inefficient.
Which is why MPC is the mandatory core of VCU 3.0. Because it's a MIMO strategy that treats the vehicle as a single complex system.
Yes, it's a fundamentally different approach.
So walk us through its operation. How is it so different from a simple feedback loop?
The MPC operation is built on optimization and prediction. At every time step, maybe every 10 milliseconds, the algorithm starts with a highly accurate vehicle model, often a 14 degrees of freedom state space model that captures all the vehicle's dynamics.
And it uses that model to look into the future.
It uses that model to project the vehicle's behavior over a future time period, what we call the prediction horizon, which is typically 300 to 500 milliseconds ahead.
And then what?
Crucially, it then solves a complex mathematical problem, a quadratic programming optimization, to find the single best sequence of four-wheel torque commands that minimizes a defined cost function over that entire future horizon. It's optimizing the whole path, not just the very next step.
That sounds incredibly computationally punishing. The payoff must be huge. What are the core advantages?
The first, and this is the game changer, is explicit constraint handling. This is the mathematical brilliance of MPC. You don't rely on clumsy truncation. You encode physical reality directly into the optimization problem itself.
So you can literally tell the algorithm the rules of the world.
Yes, we can tell the QP solver. Find the optimal torque commands to maximize yaw rate such that the commanded torque is within the motor's capability, and the resulting rear wheel side slip angle never exceeds 5 degrees, and the total power draw remains below 80 kilowatts. This multi-objective, hard constraint management is mathematically impossible for PID.
And the second advantage?
Its proactive capability. Because the controller is always predicting the future state, it can anticipate instabilities before they happen. If its internal model projects that the car is going to enter an excessive side slip state 200 milliseconds from now, the MPC starts adjusting the torque distribution immediately.
It's acting before the driver even feels the problem.
It intervenes smoothly and proactively, preventing the physical instability from ever fully developing. This allows the driver to stay at the limit for longer, which yields faster, more consistent lap times.
So the intelligence of this MPC system really manifests most clearly in adaptive torque vectoring. We're moving TV from just a simple anti-slip aid to a dynamic, predictive stability system.
Right. And to manage that complexity, we use a structured, layered approach.
A layered control architecture.
We use a hierarchical architecture. At the very top is the high-level planner, which is the MPC. This planner takes in the driver's intentions from steering and pedals, and the car's current state from the IMU. Its output is strategic. The total required longitudinal force, 5 SAURs, and the total yaw moment, MZA.
So it's the big picture thinker.
It handles the long-term predictive optimization. Below that, you have the low-level allocator. This layer is the executioner. It takes the required $5 and UMZ from the MPC and distributed them to the 4 individual inverters.
And that allocation has to be very precise.
It's mathematically critical. It has to strictly account for the current tire vertical load, which changes dramatically as weight transfers in a corner, and it has to ensure the requested forces remain inside each tire's specific friction circle limit.
So it prevents the system from asking the tires to do the impossible.
Which is often the cause of a driver losing control.
Exactly.
Now, the cost function, $. This is essentially the mathematical representation of the team's entire driving philosophy. You're trying to minimize this value to maximize performance. Can you break down the key parts of that rather intimidating formula? Of course. The cost function really just defines the trade-offs. The first term is the tracking term. This is all about performance maximization. It measures the error between the desired yaw rate, how fast the driver wants to turn, and the measured yaw rate. Minimizing this means the system works hard to make the car perfectly match the driver's input.
In the second term.
The second, and perhaps the most vital term, is the stability term. This term looks at beta, the side slip angle, the difference between where the car is pointed and where it's actually going. This term is the safety guardian. We penalize large side slip angles.
So if the car starts to slide, this term in the equation becomes exponentially large.
Precisely. And this is the core insight. When that side slip angle starts to approach its physical limit, the weight associated with the stability term is often dynamically increased, forcing it to take over the optimization.
So the math itself forces a priority shift.
The MPC is mathematically compelled to shift its priority from maximize yaw rate to minimize side slip angle. This is the automatic, smooth intervention that happens right at the brink of losing control without the driver needing to panic.
And the final terms, the control and rate terms.
Those are for engineering quality. They penalize excessive torque commands and jerky, discontinuous changes in torque. This ensures energy efficiency, smoother drivability for the driver, and prevents high-frequency wear on all the mechanical systems.
This whole optimization relies on the limits we set. But you mentioned fixed limits are not competitive. The side slip limits themselves have to be dynamic. Why?
Because the environment is dynamic. If you set a fixed limit, say 7 degrees, you're either leaving performance on the table when the track is perfectly dry and the tires are hot, or that same limit is utterly unsafe if a sudden rain shower hits.
So the VCU 3.0 has to allow for dynamic limits.
It must. On dry asphalt, we might use a wider range, 6 to 8 degrees, to let the driver really exploit the car's lateral capability. On a wet track, that limit has to be tightened aggressively, maybe down to 3 degrees, forcing the MPC to intervene much sooner and more conservatively.
But the deeper challenge is that the vehicle model itself, the model the MPC relies on, is only as good as its inputs. What happens if the tire grip changes rapidly?
That is the ultimate competitive frontier. The single most sensitive parameter in the vehicle model is the tire cornering stiffness, which we call SALFA. It defines how much lateral force a tire can generate for a given slip angle.
And that changes all the time.
Drastically, based on temperature, pressure, wear, surface friction. If the MPC is operating with a flawed static value for SALFA, it will either request too much torque, causing a spin, or too little, leaving speed on the track.
So the VCU needs to perform real-time model adaptation.
It has to. The VCU must run an observer, specifically an extended Kalman filter, EKF, or a recursive least squares RLS filter. These are estimation algorithms that use the measured vehicle dynamics, yaw rate, acceleration, steering angle, applied torque, to estimate the true value of SALFA in real time.
And then it feeds that updated value back into the MPC's model.
Exactly. It updates the model matrices. This ensures that the control system is always using the most accurate representation of the vehicle's current physical state. It keeps the torque vectoring optimal, whether the tires are cold at the start line or boiling hot at the end of the run.
Let's shift gears to the endurance event, all 22 kilometers of it. This is usually the highest weighted event, and a failure here can ruin an entire competition. How does VCU 3.0 use its predictive power to conquer this unique challenge?
Endurance completely transforms the racing problem. It's no longer about the fastest lap, it's about the fastest average velocity under a strict energy constraint.
Right, you have to finish with a certain amount of battery left.
The objective is to maximize the average velocity for the full 22 kilometers, while strategically ensuring the battery state of charge finishes at a defined minimum margin, typically around 5%, for safety.
And you can't rely on the driver's instinct to do that.
You must use prediction. The mechanism begins with track segmentation. Using GPS data and track maps, the software divides the track into specific zones: straights, heavy braking zones, hairpins, high-speed S's.
And then it allocates energy to each of those segments.
That's the second stage, energy allocation. The MPC, using its dynamic model, calculates the optimal energy needed for each segment. It simulates running the whole race at maximum power and checks the end-of-race SASE prediction.
And if it predicts you're going to run out of power before the finish line.
That triggers the third stage, active power limiting. Instead of relying on the driver manually easing off the pedal, which is imprecise, the VCU proactively calculates and imposes a system-wide optimal power ceiling. If the calculation shows 70 kilowatt is the most power we can afford to spend, the VCU imposes that cap.
So it's strategically conserving energy where it makes the most sense.
Infinitely more efficient than a driver guessing when to lift and coast. It might subtly conserve energy on a long straight so that it can allocate maximum power for a critical corner exit where the time gain per kilowatt is much higher.
Beyond raw electricity, there's the thermal constraint. That's the hidden killer of an endurance run. Batteries don't just run out of energy, they overheat.
The physics of the battery dictates this requirement. As a battery heats up, its internal resistance increases. Since power loss is proportional to the square of the current, I squared R high current draw creates exponential thermal losses.
Which can lead to the BMS just shutting everything down.
A hard DARA rating, or worse, a complete unrecoverable shutdown. Those are race killers. They destroy consistency and lap times.
So VCU 3.0 has to predict not just if it will run out of electricity, but if it will run out of thermal headroom.
Exactly. It must integrate a sophisticated thermal constraint model. The MPC's state vector has to explicitly include the battery temperature as a constraint variable.
And that enables proactive derating.
It does. If the MPC predicts that a few upcoming high-load acceleration zones are going to push the battery temperature past a critical threshold, say 55 degrees Celsius, it will subtly lower the power ceiling right now before it becomes a problem.
So you get a small, consistent reduction in power instead of a catastrophic shutdown mid-corner.
It's about maintaining overall speed and consistency, which is a huge, often overlooked competitive advantage.
We have to bring this all back to the foundational principle. All this performance is built on a foundation of safety and compliance.
Absolutely. The VCU is the digital gatekeeper. It must ensure the car adheres to every letter of the rulebook.
Let's start with the driver interface. The accelerator pedal position sensors, the APPS, and the plausibility checks.
Rule T11.8 requires absolute redundancy. The VCU has to monitor 2 electrically isolated pedal position sensors. The recommended best practice for implementation is to use an inverse transfer function.
So as one sensor's voltage goes up, the other goes down.
Sensor 1 goes from 0.5 V to 4.5 V as the pedal is pressed, while sensor 2 simultaneously goes from 4.5 V down to 0.5 V. This inverse relationship gives you instant, robust fault detection. Any electrical noise or a short-to-ground failure becomes immediately obvious.
And the failure logic has to be instantaneous.
It must be absolute. The ATPS failure logic mandates that if the 2 sensor readings deviate by more than 10% for more than 100 milliseconds, the VCU must immediately and non-recoverably set the torque to 0. And this entire check has to be implemented as a highest priority task. It's an interrupt that cannot be blocked by the MPC computation. Safety trumps performance, always.
Now, what about the brake system plausibility device, the BSPD? The physical one is a hard circuit. If it fires, your race is off and over.
The physical BSPD is a blunt instrument. If brake pressure is high and power output is high, it fires a hard shutdown. That's a race ender.
So how does VCU 3.0 implement a smarter, more recoverable approach?
It implements a sophisticated shadow BSPD. The VCU software runs the exact same logic check as the hardware device, but much, much faster. If the VCU detects the conditions that would trigger the hardware BSPD, it proactively zeroes the torque output, say 50 milliseconds, before the hardware device would even have time to react.
So it's a software fuse that trips before the hardware one does.
Exactly. This is a recoverable intervention. By zeroing the torque quickly, the VCU prevents the high current draw that trips the physical safety circuit. The driver feels the power loss, but they can instantly recover control by releasing the brake or throttle. You avoid the catastrophic hard stop.
And finally, there's system critical signal monitoring.
Right, Rule T11.9. It's not enough to just read a sensor's value. You have to ensure the wiring and the sensor itself are intact. The VCU must actively check inputs pedals, steering, brake pressure for open circuits, shorts to ground, or shorts to power.
And if it finds one?
Upon detection of any of those faults, the mandatory response is to enter a predefined safe state. This usually means instantly setting the torque to 0, activating safety indicators, and maybe entering a restricted limp mode to allow the driver to safely get off the track. The VCU is not just a performance tool, it is the ultimate safety guardian.
For a new team adopting this highly structured VCU 3.0 spec, the development process is just as important as the requirements themselves. You've stressed that a team has to adopt the model-based design workflow, guided by the classic V model.
The V model is essential because it guarantees traceability. You design a requirement on the left side of the V, and you must rigorously test and validate that exact requirement on the right side of the V. It ensures you don't find a catastrophic bug for the first time on the track.
And you break this process into 3 critical stages. The first is model in the loop, or MIL.
Stage 1 is MIL. This is pure theory and simulation. The team builds the complete dynamic vehicle model and the MPC controller entirely within Simulink. No code is generated. The focus is purely on validating the logic. Does the theory work? This is the cheapest and easiest stage to find and fix conceptual errors.
Once the concept works, you move to testing the actual code.
That leads to software in the loop, or SIO. Here, we generate high-quality C or C++ code from the validated Simulink models. The goal is no longer physics validation, but code execution efficiency. We test the generated code on a standard PC.
And what's the key metric you're looking for there?
Performance quantification. We must ensure that the computationally intensive parts, specifically the quadratic programming solver, often an open-source tool like OSQP, can reliably converge on a solution in less than 1 millisecond. If the solver takes 1.5 milliseconds, the entire 1 kiloverse control loop is instantly violated. You know you have a problem before you ever touch the hardware.
And the final step before the car hits the track is hardware in the loop, or HIL. This is where we subject the actual VCU hardware to a simulated reality.
HIL is the integration test where the rubber meets the digital road. We deploy the SIL-validated code onto the actual VCU hardware, the SpeedGoat, for instance. That VCU is then connected to a real-time simulator which feeds it voltage signals representing all the car's sensors.
And for a new team, the focus of HIL should be on resilience testing.
Absolutely. This is the only place you can safely inject catastrophic failure scenarios. We deliberately simulate sensor failures, shorting a brake pressure sensor to ground to verify that the safe state logic engages correctly. We test the EtherCAT drivers by simulating packet loss. You test stability by commanding the virtual car into a huge slide at 120 kph and confirming the MPC successfully recovers it.
So HIL is essential for proving the safety systems are robust enough for the chaos of a real race. And then finally, you link this all back to the actual competition events.
The final step is using the competition events as calibration benchmarks. Skid pad testing is a pure calibration exercise for tuning the yaw rate tracking parameters in the MPC cost function.
Acceleration testing is for calibrating the traction control.
Exactly, making sure you maximize launch grip without excessive wheel spin. And finally, endurance testing is the comprehensive validation. This is where we verify the complex energy management model and the thermal limiting logic. If your energy prediction is off by more than 2% over a long run, the model has to be refined.
So to summarize this entire VCU 3.0 strategy,
The document is the technical path from simply participating to winning. It mandates EtherCAT for deterministic communication, it transitions control philosophy to model predictive control for multi-objective optimization under strict constraints, and it embeds critical safety compliance into the heart of the system architecture.
so what does this all mean? The VCU is absolutely no longer a passive switchboard. It's an intelligent, proactive conductor that operates at the very physical and energy limits of the vehicle, maximizing performance while guaranteeing compliance.
And by adopting this rigorous architecture and the structured V-model pathway, the team isn't just building a fast Formula student car. They are rigorously training a cohort of engineers with a world-class understanding of future automotive SDV technology.
The exact skill set needed for the next generation of electric mobility.
But the greatest competitive challenge for any team implementing this, it remains the accurate real-time estimation of those critical tire parameters, specifically the cornering stiffness, CC alpha, in dynamic conditions. If your vehicle model is supplied with inaccurate static tire data, the most powerful MPC solution in the world is, quite literally, solving the wrong mathematical problem.
The optimal strategy is only optimal relative to the model.
Precisely. So the question to leave you with is this. How can a new team best leverage inexpensive, non-proprietary sensors and advanced filtering techniques, those EKFs and RLS filters, to continuously measure and adapt to the true real-time extent of the tire's available grip? That dynamic adaptation, that is the frontier that will determine the champions of tomorrow.